Hello and welcome to SPEE3D. My name's Byron Kennedy and I'm the CEO of SPEE3D. So today, what I'm going to do is take you through a walking tour of the facility here in Melbourne, Australia. So in today's world, it's quite usual to wake up and have 4 to 5 Zoom calls or Skype calls planned across your day. And the Zoom calls could be with the person in the next room, they could be in the person in the next city, the state or country. So I think what it's done here is it's actually bringing the world together and it's a much smaller place than it was pre-COVID. So today, as I said, this walking tour is going to be from Melbourne, Australia. And we're going to show you the printer technology which we produce, how we produce the printers. We'll also then cut in some footage of showing the printers in action, not just in the facility here, but in the field. So these printers which we're selling today, so these are metal-based 3D printers. They're actually being used in not just in a production environment, not just in a lab environment, but actually in the middle of the bush. So the Army, for instance, the Australian Army have used one of these printers. They've taken it out into the middle of the bush, set it up, and printed parts in the middle of essentially nowhere, in the middle of a simulated combat zone. So what we're doing is proving that this technology is robust, reliable, can be put on the back of a flatbed truck and used anywhere in the world. So where is this important? It's important in those heavy industrial applications, defense, mining, oil and gas, anywhere where you're concerned about, having access to good power. All of these things we've taken care of with this particular technology. So today we're going to take you through and show you the inner workings of how we produce the machines, what the machines can do, and also the post-processing. So we'll print some parts. We'll show you how easy it is then to remove the parts and then to post-process them and to get them into essentially a final state. The printing is very, very fast. So typically, small parts like this will be printed in less than 10 minutes. So the beauty about this process is you can see the start. So you can see it's loading the powder, then printing the parts, and you'll see the whole process in 10 to 15 minutes. And we'll demonstrate some of that today with you as well. So let me take you back and talk about the company, what we do and where we're going as a company. So I'm one of the founders with Stephen Camilleri, and Stephen's actually based in Darwin. So the Speed office you see here today is our manufacturing facility in Melbourne, Australia. We also have an R&D office in Darwin, so they do all the development, and then sales offices in Germany and the US. So we are truly a global organisation. And outside those regions, we have resellers. So we have resellers in Asia, into Africa, into South America. So we're actually covering the whole globe. The only continent we don't have a dedicated reseller is into Antarctica, but I'm happy to go down and do that myself if required. So we are there to support you in sales and after support service, and we'll be there to support you and help you with the use of the technology. So what we're going to do, as I said, is we'll have a look at some of the machines, the inner operations of the machines, how they work, and where they can be used. We'll also talk about activated copper, and this is an antimicrobial copper, which we apply to common touch surfaces such as door handles, push plates, and the like. And that's used to then, and it's been proven to kill the COVID-19 virus. So this is what we did in response to the COVID-19 virus. And we thought, how could we help? Well, we developed the activated copper. So we'll take you through that process. We'll show you how it's a coating process. It's economical. It's fast. It's low cost. It can be rolled out now, and it is being rolled out now. So let's go out and have a look out the back. As I said, we'll look at the different printer technologies. We'll get behind the scenes. You'll see some of the manufacturing. We won't show you everything, but you'll get a good overview of where we are. And then after, we'll happy to answer any questions. So let's go out. So every 3D printing technology needs some sort of ancillary components, and at SPEE3D we're the same. So the ancillary components required to run the printer is very simple. Two things: we need a compressor and a dust extractor. And therefore, you know, in a normal site, you might just put a compressor and a dust extractor in, or you may package it up. And what I'm going to show you here today is what we call speed core. And this is where we package up the dust extractor and the compressor into a 10-foot shipping container, which you can see behind me. Now, the advantage of this 10-foot shipping container, which we call speed core, is that one, it is transportable. So if you're at a defence organisation, mining, oil and gas, one of those heavy industries, and you may want to move your printer and accessories around, this is a very convenient way to do it. You simply get a forklift and move the printer and also the accessories in one part. The other important point to note about the speed core is that often when you're putting a printer in, the ancillary costs can be very, very expensive for a standard metal 3D printer. Now, in a speed core, this is all packaged together, so you don't have to go through a lot of OH&S issues, a lot of compliance issues, because this is all covered in this one box. So let me take you inside the speed core and explain what we do, how it operates, and just to give you a feel of what's inside. So we'll start over here with the compressor. So you can see, I'll just open this up. What we have here is a standard compressor which is used to run the printer. So this is a 30 bar compressor. So it's mounted in here, it's serviceable, it's accessible, it has airflow, and it's just a simple way to package this compressor. So that, as you can see from the outside, you can service it from the outside. So let's now go inside the speed core and we'll see what's inside. So as I said, standard 10-foot shipping container. Just opening up this now. So what we have inside the speed core, so as I said, the compressor unit sits under here. That's an accumulator for the compressor, and the various compressor accessories are built into this side of the speed core. On this side of the speed core, we have our dust extraction system. So in this printer, not all the powder that we spray sticks. So, you know, roughly it could be 90% of the powder that you spray sticks. So you do have some powder which is floating around in the printer chamber, and we then collect that in the dust extractor, which you see on this side. So the speed core incorporates all of the requirements for the accessory components that are required to print parts. You can drop this either, you know, outside your facility. You can drop it in a mine site, at a defence organisation site. So very, very easy to install. As you can see, you just simply use a forklift to drop it in. You have a tube which is going to come out for your dust, and then you have a high pressure tube for the air that goes to the printer, and that's all. So you'll find that the installation you can do in less than a day. So before we start printing, I want to describe how the process actually works. When we start the printer, there is some background noise. So the dust extractor makes some noise, the compressor makes some noise, and the printer makes some noise. So it's a bit easier to explain before we actually start the printing process, how it actually works. So come over here and I'll show you what's inside the printer from a high level point of view. So the black part there is the rocket nozzle. And what the rocket nozzle does, it actually accelerates metal powders up to supersonic speed, so about Mach 3 or about 1,000 meters a second. We then spray that powder up, and then it hits a surface. That surface we call a substrate, which we mount on the back of the robot there. So the substrate's not mounted on the moment. We will mount that, and then we will print a part next. The build chamber is what you're seeing now. So it's stainless steel build chamber, and that collects any powder that doesn't actually adhere during the printing process. So typically most of the powder does stick, but some of the powder does not, and then we collect that in that dust extractor which we explained before. Alright, so we've got about a minute left now in the printing, so you can see the screen here gives you some information about the print. So as I said, we've got about just under a minute to go. Shows you pressures, temperatures, the amount of powder you have in the machine, state, etc. So that just gives you a little bit of feedback on what's happening during your print, as well as the video showing how part's nearly done, so it's just under 15 minutes to be able to produce this part, and the part's just nearing completion now. Alright, so that's the whole printing process complete. So you can see here, just some feedback on the print time, etc. So this machine is now cooling off. It takes about a couple of minutes now to cool down. And once it's cooled down, we can then open the door and then pull the part out. So I will show you that in a moment. Alright, so now the printer has cooled down. It takes about a minute, so we cut that part out. And now all the interlocks are off, so it says, yes, you're now safe to open this machine. So you simply hit the unlock, you then come over here, pull these two handles, and that's it. So we have a couple of clips on the substrate, which enables us now to pull this substrate off. And that's it. So the part itself is relatively warm, so it's about 60 or 70 Celsius, so it's certainly not burning hot, but we do use the gloves just for safety. So you can see that's just pulled straight out of the machine. You can see the machine itself, after a print, there's just a little bit of residue powder around, but not very much, so it's a very clean process. Any powder that didn't stick was then extracted and then collected in the dust extractor, which I showed you early on. So now what we'll do is I'll take you over and show you how we actually pull this off the substrate, because that's a question that we get asked many, many times. All right, so here's the completed wheel that we just printed. So as I said, the next step is you need to remove that from the substrate. So typical in 3D printing, you use an EDM process or some very expensive and long process to actually move the parts. Our process, very simple. Everyone has one of these. Everyone has one of these. A couple of taps. And the part's removed. Alright, so what I'm going to do now is show you the actual manufacturing of the printers. What you see behind me here is one of our warp speed machines. So as you can see, it's only partially built. Interestingly, all of our final built machines have all been shipped in the last few weeks. So I'm not actually able to show you the operating warp speed machine, but we will show some footage of the machines operating in the field and how they've actually been used in the middle of the bush. So the machine itself, you can see stainless steel and steel frame put together. You can see in this machine the much larger robot which we use. So as I explained earlier, there's two differences. There's one major difference, between the two machines, the light speed and the warp speed. And that's the size of the parts that can be built. So the light speed, which is printing that wheel which we saw earlier, prints parts up to about 10 pounds, 4 kilos, and about a foot by foot, where the warp speed produces parts up to just roughly 100 pounds and about a metre or 3 foot in diameter by about 2 foot or 700 tall. So the difference is really the robot. So you can see here a much larger robot, and also the build chamber. So the build chamber is what effectively limits the size of the parts. And this build chamber is taken out to the maximum that we can actually fit within a shipping container. So what the purpose of the design was to say it needs to fit into a shipping container to make it easy to transport around the world. Because as I said, this facility here you see is in Melbourne, Australia, and we're shipping these printers worldwide into Germany, into the US, into Japan, South America, etc. So it needs to be easily transported. So it's actually being designed to fit within a shipping container, make it easily transportable. And that therefore limits the size of parts that we can produce to about a metre diameter. So there's no physical limitation why we can't produce bigger parts. It's simply designed around what's easy to transport around the world.
Hi, my name's Phil Bowles. I'm the Chief Operating Officer of SPEE3D, and what we're going to show you today is the speed cell. So we're starting with our light speed machine, as Byron's already mentioned about the two types of products we have. So this is our light speed machine that does typically the smaller components. And the natural life cycle of a printed component is going from manufacture, so from print, and we come over to our heat treatment furnace that we have here, where we would get a component such as this small pulley that's been printed out of aluminium bronze actually. In the light speed machine, it's been heat treated in our furnace, and the next step of operation is moving it into a machining centre, or it could be a CNC lathe, depending on the type of component that you need to manufacture, and where it would obviously be machined for whatever features, taking off the machining margin, drilling and capping holes, whatever it is that needs to be done. So that's the displaying the full life cycle of a component coming from basically printing something from fresh air, heat treatment, and then with some finished machining.
Right, so now I'm going to talk about some applications. So you've heard about how the printers work, you've heard about the accessories and the post-processors. So now, what are some of the applications, activated copper being one of them, and now also let's look at parts. So parts production is what the printer was actually designed for, of course. The coating technology, interestingly, came second. So we designed the printer to be able to produce parts, of course. Then we developed the activated copper in response to the COVID-19 virus. But it's very, very interesting now that we have a printer which can actually build parts, can code parts, and next, it's going to be able to repair parts as well. So the one technology will be able to do all three things. And the repair will be the integration of a scanner. So that's coming, so stay tuned for that one. So let me talk about some of the applications. Materials we print, typically copper, aluminum, bronze, stainless steel's coming, and some more materials. So copper's a very interesting material that we can produce very, very quickly and at very, very low cost. So typically copper is a high cost material and it's not used. Now in powder form, however, copper is actually remarkably low cost, and it's a material that we print with very, very quickly, as I said, and therefore because the powder's a low price and the printer is very, very fast, you can produce parts very economically. So where is then copper used? So copper's typically used in two or three major applications, one being thermal application, it can get rid of heat very easily, and also electrical applications to transmit power from one point to another. So let's talk about thermal applications, and I have three examples which I'm going to show you here. So the first is heat sinks, traditional heat sinks. So what is a heat sink and how is it used? A heat sink takes heat from one point and then removes it from that source and then dissipates it typically into free air. So as an example, if you have electronics and electronics gets hot, you'll mount it on a heatsink to take that heat away from the electronics. So in this example, what we did is we got extruded aluminum fins, which you can see here, this L-shaped fin. We then cold sprayed, using our process, the copper onto the surface of it. Now, why would you do that? Why would you not just extrude a straight aluminum heatsink? Well, copper removes heat faster from that electronic component than aluminum. And so what we've done is we've used the best of both worlds. So traditional extrusion of aluminium fins, which are cheap and low cost, and then we use our process to put the copper on, which is very effective for moving the heat away from the electronic source. So what you're producing here is an improved heatsink at a very economical price. Second, let's talk about water cooling. So water cooling is the most effective way to keep electronics cool. So what we have here is that just is a water cooling block. So you can see here, if I pull this off, we actually have, I'm not sure if you'll be able to see this, but there is a enclosed channel in there. So in this particular example, you mount your electronics onto the top here, you then put water around this surface, comes out here, and it's a very effective way to have an enclosed channel for water cooling of electronics. So that's the second example. The third is being able to have manufacture a pin heatsink. So we have a method to be actually manufacture these very fine pins, and we do this very, very quickly. So you do this in about 2 minutes. So what's the best way to cool electronics is some sort of pins. The best material is copper. So a copper pin fin heatsink is the third example in terms of thermal applications where this technology does suit. All right, the second example that I want to talk about today is parts for defense applications. Now, it extends beyond defense, could be mining, oil and gas, and other applications as well. This is what's called a camlock fitting. So a camlock fitting is essentially a hose fitting. In this instance, it's used in transporting fresh water around a naval vessel. So this is made out of aluminum. You can see here, it's what they call a Christmas tree. So that's aluminum and then followed by 2 stainless steel fittings. And what happens is there is an issue at the junction between the aluminum and the stainless steel, and you get a corrosion point, and these aluminum fittings then corrode out. So the Australian Navy talked to us and said, can they just print this part? And we said, well, you can print that, but why not print the whole thing? Because then you get rid of your Christmas tree, what they call it, from aluminum to stainless, and then you can print that in one part. So straight off the printer, we've just printed this one. We haven't yet machined it up, but that was straight off the printer. So you can see roughly the same size and shape. And what we're now doing is being able to reduce the weight and improve the reliability of the part. So this will go through some final post-machining where you simply put that thread onto it and clean up the inside, and that's a part then ready for use. So it took about 25 minutes to print something like this. So what I'd like to do now is talk about activated copper. So activated copper was our response to the COVID-19 pandemic. So what we said is, when the pandemic hit, what can we do to help? We knew of this property of copper, which is that it's antimicrobial. So what that means is copper actually kills viruses and bacteria upon contact. So we thought, would it actually work on the COVID-19 virus? So what we did is we developed activated copper, which is a copper material which we spray onto an existing part to be able to produce an antimicrobial layer. So as an example, this is a door handle. So door handle is a very, very common touch surface, of course. You need to be able to push or pull on a door handle. So what happens in terms of viruses and bacteria, if you've got a virus and bacteria on your hand and you touch a surface, you can transmit that bacterial virus onto that particular surface. Now, the property of activated copper is it actually kills the bacteria or virus. And what we did is we went out and clinically proved that we would kill the COVID-19 virus, or 96% of the COVID-19 virus, in less than 2 hours. And that was the activated, and that is our activated copper product. So let me show you where this technology is actually being used today. So it's used on common touch surfaces. So think in things like, this is just an example, in a rail application or on a bus. And on those applications you have handles which you need to then hold on to. So what we can do is take a standard grab rail, so this is just a section of it, of course. You can then coat it in copper like this. So this is straight off the machine. You then finish it to produce a nice shiny finish with something like that. And that then is an antimicrobial surface which is then used to kill bacteria and virus. The properties that we get out of the copper is very, very good. So copper is typically quite a soft material. It's typically very hard to electroplate, so you can only put very, very fine layers of copper on at the moment. And electroplated copper is very, very soft. So one of the properties of our copper is that it's hard. It is very, very hard because of the cold working that we get during the deposition process. So this layer of copper is very, very tough. And what that means is that then it will withstand a lot of punishment over time. Because when you put a coating on a surface, especially in a high touch surface area, it's going to get a lot of punishment over years and years and years of use. So, putting a thin layer is no good. You need to put about 0.5 millimeter to 1 millimeter material on, and we can adjust the height, of course. So there's a bit of copper on that one. This one has a thinner layer. And it shows you other surfaces here. So how it actually works is and this is a typical a push plate. So a push plate might be used in a toilet door or something like that. So stainless steel push plate, and what you're doing to open a door is you're pushing on that plate. So we take a standard stainless steel push plate, we then coat it in about 0.5 millimeter of activated copper. So you can see on the back here, you can see the stainless steel, and then this side it's been coated in about 0.5 millimeter of the activated copper. You then polish that, and then you get this as the final product. And what that is activated copper, which is used then to kill bacteria and viruses. All right, I'll also talk about the multi-material capability of the printer. As you can see here, what we've done is printed the Speed logo, which is copper, and we've printed that onto aluminium. So the printing technology enables us to print a variety of materials in a multi-material way, which has not been done before. So we can put copper onto aluminium, you can put copper onto steel, you can put aluminium onto different materials. So it actually opens up a whole world of opportunities of being able to join materials, coat materials, repair materials, that in traditional technology is very, very difficult. So let me finish by talking about our Thor hammer. So the Thor hammer, is this a real world application? Maybe not. You know, there's a small market for Thor hammers out there. But the important thing about the Thor hammer is actually the time it took to produce this. So this is 8 kilograms, and it takes about 80 minutes to print this. So we print this in a very, very short period of time, and it's quite heavy, as you can see here. I'm not quite the Thor out there, but it's very, very fast, and we're able to produce this, as we said, very quickly. It's produced off our warp speed machine. You simply have to post machine the surface to get it nice and polished, but otherwise it's then ready to roll. So thank you for joining us today on a tour around SPEE3D's Melbourne facility. As I said, we're here to support you wherever you are in the world, be it the US, Europe, South America, or anywhere in Asia or Australasia. So for more information about SPEE3D, please go to our website, SPEE3D.com. Have a look at the YouTube site. We have some fantastic videos of actually printing parts. I've given you a little bit of a snapshot of the parts we produce, the technology, the background. We'll also be happy to answer any questions after the virtual tour today. So thank you very much, and enjoy the rest of the meeting. Cheers.